Hey everyone, welcome back to Abstract Algebra 1. This is going to be lecture 9 of the course. And in this section, we're going to discuss Lagrange's theorem. And Lagrange's theorem, it's one of the biggest theorems in group theory. And the proof of Lagrange's theorem is going to come very quickly via the concept of cosets. And so we're going to discuss cosets as well. Let's go ahead and jump into it. We'll call this section 2.7, cosets and Lagrange's theorem. And we're going to start with a definition of a coset. All right, so let's let G be a group, okay, and H a subset of G. Okay, so we've got a group G and H is some subset of the group. Then for any element in G, we'll call it A. For any A in G, the set A times H such that H is in the subset H is denoted by A times capital H here. Okay. Okay. And analogously, we could define a set similarly with the multiplication being done on the opposite side. So I'll just say analogously, H times A, capital H times A, equal to the set H times A such that H is in H. And we could also do something like this, right? A times H times A inverse is equal to A, H, A inverse such that H is in H. All right. Now, these sets, so defined, so when H is a subset of G, the sets A times H is called the left coset of H in G. Now, technically, we would say containing A. Okay, this would be the left coset of A. Right, so the one we defined at the onset, A times H such that H is in H. That's called the left coset. And then, of course, the other ones as well. Here, this would be the right coset. Okay. Now here, in this kind of a definition, A, the element A is called the coset representative. It's called the coset representative of AH or HA, depending on which one you're talking about, left or right. Okay, so this is what we mean by a coset. Okay, so any subset in a group G, you can define these sets, right? Now, when H is a subgroup of G, then you get cosets. Okay, if you're pulling from if H is a subgroup of G, then A times H is going to be the left coset of H. H times A is going to be the right coset of H. Okay, this is the idea of a coset. All right, now let's do an example. See if we can make some more sense of this through an example. So let's let the group of interest equal S3. Okay. And let's let, so what is S3? S3 is the symmetric group. It's a group of permutations on the set Remember 1, 2, and 3. That's why we call it S3. It's a symmetric group. It's the group of permutations on the set 1, 2, 3. And let's let H equal a subset of S3, namely the subset of 1 and 1, 3. These are permutations inside the group S3. Okay, and so let's see what, let's look at the left cosets of H. Let's enumerate them all. Let's write them all out. Let's write out the left cosets of H in G. Okay, so if I've got my coset, my subset H, which is 1 and 1, 3, and I multiply it by 1, well, then what do I get? Well, 1 times any permutation, 1, so it would be like this. I would have 1 and 1, and 1 and 1, 3. Now what does this resolve down to? Well, of course it resolves down to just 1 and 1, 3. Which is just H. Let's look at a more exciting example. Let's look at 1, 2. Again, 1, 2 is an element of G, right? So it's an element of G, and we're going to multiply it by all the elements of H. And so I get what? 1, 2, and 1, and then 1, 2, and 1, 3. Okay, so what happens here? Well, we can simplify these, make these disjoint. So 1 comes in, it goes to 2. 2 comes in, and it goes back to 1. So you can see that that's closed. And then what about this other one? 1 comes in, it goes to 3. 3 comes in, it goes to 1, which goes to 2. 2 comes in, and it goes to 1, back to 1. So it closes up. Okay, so this is the left coset of H containing 1, 2. Okay. What about 1, 3? Another element in G. So it would go 1, 3 times 1, and then 1, 3, 1, 3. And what happens here? Well, I just get 1, 3, don't I? So 1 comes in, and it goes to 3. And 3 comes in, it goes back to 1, so that one closes. What happens here? Well, 1 comes in, it goes to 3, which goes to 1. All right, so it actually closes up just like that. Okay. Let's try one more. We'll do 2, 3. Okay, so you get the 2, 3 times 1, and then 2, 3 times 1, 3. Again, just taking this element 2, 3 times all of the elements in H. H is 1 and H is 1, 3. Right, so that's what we're doing. And so this one here resolves down to just 2, 3. And this one over here resolves down to 1 comes in, it goes to 3, which goes to 2. And then 2 comes in, it goes to 3. And 3 comes in, it goes back to 1. Okay. Now it turns out that for these three, if we were to continue and exhaust all of the elements of G, you'd find that there were exactly 3 more, right? And it turns out that with this one, another element that we haven't looked at yet is 1, 3, 2. And it's actually the same as 1, 2. 1, 3, 2 H is the same as 1, 2 H. All right? And this guy here resolves down to just H again. Obviously, you can see that. But then this one here captures 1, 2, 3 H. All right, so if you did the same exercise with 1, 2, 3 H, you would arrive at the same set. Okay, and these are all of the combinations. These are all the different permutations of 1, 2, and 3. So you have the 1, the 2, and the 1, the 1, 2, the 1, 3, the 2, 3, the 1, 3, 2, and the 1, 2, 3. Right? So they're all here plus. Right? So everything is in here, and these are the cosets. Right? So really, you'd think of this as a coset, This is a coset, coset, coset. Okay, so that's kind of a nice physical example to get you started thinking about this. Let's look at another one. Let's look at another example. Okay, here we're going to talk about the dihedral group. So let's let K equal the 0-degree rotation and the 180-degree rotation in D4. Okay. Now remember, D4 is the dihedral group. It's the dihedral group of order 8, I guess. Okay. Let's look at the cosets related to this subset of D4. Okay. So let's start with R0 of K. Well, that's going to be R0 times R0. And then it's going to be R0 times R180. I'm saying times, I know this is actually composition of functions. But you can see that this is basically going to just give us right back K. So nothing interesting happens here. What about R90? Well, that's R90, R0, R90, R180. And what happens if I do a 0-degree rotation followed by a 90-degree rotation? Well, it's equivalent to a 90-degree rotation. And what happens if I do a 180-degree rotation followed by a 90-degree rotation? That would be a 270. Okay. And it turns out that this set here is actually the same as R270 of K. Right, so R270K. So if the left, this would be the same as the left coset of K in D4 containing R90 is equivalent to the left coset of K in D4 containing R270. Right, you could just see, you could just do the exercise. Right, maybe it's enough to look at it and think it through. What about R180? Well, again, that's a 180-degree rotation following a 0-degree rotation, and then it's a 180-degree rotation following a 90-degree rotation. All right, and here you're going to get, well, if I rotate 0 degrees and then 180, that's an R180. And then if I rotate 90 and then 180, that of course is, oh, sorry, typo. This should be 180 here. I apologize. 180 and a 180. That's going to give you back an R0, isn't it? Yep. And so that one is back to K. Okay. So the rotations are fairly easy to see. What about the flips and whatnot? So let's look at a vertical flip. So that's going to be a vertical flip following a rotation of 0 degrees, and then a vertical flip following a rotation of 180 degrees. Well, you may have to draw a picture. The first one is easy, but for the second one, you may have to draw a picture, right? You do a 180-degree rotation followed by a vertical flip. It turns out that's equivalent to a horizontal flip. And it turns out that the left coset of K in D4 containing V, this guy VK, is the same as HK. Okay, and you can just check it, just test that. And then what about a diagonal flip? Well, so that's D following R0 and then D following R180. Right, and so obviously you're going to get a D there. And what is this? Again, you may have to draw a picture. But imagine doing a 180-degree rotation and followed by a diagonal flip. Right, so a flip on the main diagonal. Right, if you draw a picture, you'll see that that's D prime. And you may guess it, and you would be correct. This is equivalent to D prime. Okay. right? And so these are the left cosets. These are the left cosets of this subset K, which turns out to be a subgroup of D4. Okay? All right, so these are good physical examples. Let's do one more example here. Let's do one more example. Let's let H equal the subset 0, 3, and 6 in Z9 under addition. All right, so this is addition modulo 9. So in the case where the group operation is addition, we want to kind of change the notation a little. So if the group operation is addition, we will change the notation slightly. Well, we'll change the notation to reflect this. Right, so what we'll write instead, we'll use A plus H in place of A times H, like this, right? So this notation, right? And that's, I mean, does it really matter what you're naming the thing? Not really, but this is more intuitive if the group operation is addition. Otherwise, you start to get, I mean, these are already a little bit abstract in terms of, you know, as concepts, and then if you start to get notation that's not intuitive, it can be really messy. Let's look at the cosets of H in Z9. Okay, let's just go through it. So let's do, what's 0 plus H? 0 is an element in Z9. What do we get? Well, it's just 0 plus 0, 0 plus 3, 0 plus 6. So you obviously get the same thing. Now it turns out, and you can confirm this, but you get the same thing as well if you do 3 plus H. And you also get the same thing if you do 6 plus H. Okay, so if I were to add 6 to everything, for example, here, 6 plus 0 is 6, 6 plus 3 is 9, which is 0, 6 plus 6 is 12, which is 3, mod 9, right? So these are all the same. What about 1 plus H? Well, you're going to get 1, 4, and 7. Okay, and it turns out that's equal to 4 plus H. It's also equal to 7 plus H. Right, just adding 1 to each of these. 2 plus H. Well, that's 2, 5, and 8. And so that's going to be the same as 5 plus H and 8 plus H. And we've exhausted them, haven't we? We've exhausted them. Okay, so these are going to be the left cosets of H, which in this case is 0, 3, 6, in Z9. Okay, these are all the left cosets of H, of this particular subgroup. Okay. Right, now notice H is a subgroup, right? You have closure here. Okay. All right, very good. Now, things to note. Things to note. A couple of things. And we'll get into some properties in a second, but just a few things to note that are worth digging out or worth drawing out because they are frequently sources of confusion when people are first wading into this area of algebra. So the first thing is that cosets are usually not subgroups. Okay, so they're usually not subgroups. Okay. Cosets are usually not subgroups. Okay. Now, I mean, it's easy to see in the previous example, we had 1 plus H, for example, we saw was 1, 4, and 7. And this is not a subgroup of Z9. Okay. 1 plus 4 is 5, which is obviously not in 1 plus h. Okay, so that's the first thing to note. Second thing to note, the coset AH may be the same as BH, right? Even if A is not equal to B. And of course, we saw this already, actually. Right? We've seen this already. We saw in the previous example that 1 plus h was equal to 4 plus h. Right? Obviously, 1 is not equal to 4. So this is something that's just worth pointing out, that you could have two cosets that are the equal. They're equal in terms of the set, but they are the element that was used to generate the coset, it may not be. Those two elements may not be equal. The 1 and the 4 in this case. All right. In a previous example, we saw that R90k was equal to R270k. And obviously, R90 is not the same as R270. So we've seen examples of these already. And then the third thing to note is that AH, the left coset of H, may not be the same as the right coset of H. Okay, and we'll see when this is true and when it isn't true. But it would not be hard to go back through the examples we just looked at, and instead of looking at the left cosets, look at the right cosets and see whether or not they are all the same. Right now in the example, like up here, they're going to be the same. Right? So Z9 is a group that commutes. No problem there. But if you look at some of the permutations and the dihedral subset group example, they may not work quite as nicely. Right? There you may find that the left coset and the right coset are not equal. Okay? They can be, but they may not be. They need not be, is the way to say it. All right, very good. So that's the definition and a few examples. Let's talk about properties. Properties of cosets. Now, there's going to be about 7 items on this list, and we're going to actually prove all 7 of them just to help develop intuition about these things. All right, so let's go ahead and, because these can be kind of tricky, like they're strange objects, cosets. Right? Sometimes they're groups, sometimes they're not. They're built by groups acting, elements in a group acting on a subset, but sometimes the subset's a subgroup. They can be a little tricky. So let's go through a bunch of properties and see if we can develop more understanding here. Let's let H be a subgroup of G. Okay, H is a subgroup of G, and let A and B belong to G. Okay, then item 1, A is in the left coset of H containing A. Right? A is in AH. Okay, so that's the first one. We'll prove that. The left coset of H containing A is equal to H, right? It equals the whole subset H, if and only if A is in H. Okay, so remember, A doesn't have to be in the subset H. It just has to come from the group G, right? But if A does come out of the subgroup H, then AH will by necessity equal H, and we'll prove that one in a second. That's interesting. Okay, so then the third one says that AH equals BH, or AH intersect BH is empty. Right? So either the left coset of H containing A and the left coset of H containing B, either they're equal or they have nothing in common. So they're either equal or they have nothing in common. That's interesting as well. Okay. All right, number 4. Number 4 says that AH equals BH if and only if A inverse B is an element of H. Okay, we'll see why that works in a moment as well. Okay, and number 5, this one is very interesting and will go a long ways towards helping us in our proof of Lagrange's theorem. The order of AH, right, so the number of elements in this coset, is equal to the number of elements in BH. And this is true for all A and B in G. What this basically says is that all of the left cosets of H are the exact same size. Okay? And number 6, AH equals HA, so the left coset and the right coset agree if and only if H equals AHA inverse. Okay, so that one is probably not too surprising. We'll see. We'll prove that in a moment. And the left coset is a subgroup of G. Sometimes it's a subgroup, sometimes it isn't, but it is a subgroup of G. It is a subgroup of G if and only if A is in H. All right, so if A comes from outside of H, then the left coset of H in G containing A is not a subgroup. Okay. All right, so these are the key 7 properties for subgroups. Let's prove some of these guys. Okay, let's prove these. I'm going to just use this page right here so I can keep an eye on which ones we're proving. Okay, so we'll prove all of these. The proof of 1. So remember what we're trying to prove here is that A is in AH. Well, this one is fairly easy to do. So A, of course, is equal to A times E, right? Remember, A comes from a group G, right? So A is in A times E, and this is certainly in A times H, right? H is a subgroup by assumption, so it contains the identity. So I'll write since E is in H, i.e. H is a subgroup. Right, so A must necessarily be in AH. That one's very easy. Okay. And indeed, when we say the words, the left coset of H in G containing A, it's sort of in the name, right? Okay, so okay, what about item number 2? Item number 2 says that AH equals H if and only if A is a member of H. A comes from H. Okay, so let's prove this one. We'll start with the one direction. We'll assume AH equals H. Okay, and if we do that, then what happens? Well, then we have AE is in AH, which is, of course, equal to H. Right, so that means A is in H. Right, I guess I should write A equals AE. Okay, right, this one just kind of follows from 1. And then what about the other direction? The other direction. Well, let's assume that A is in H. We'll assume that A is an element of H. And so then by closure, clearly by closure, right? By closure, we would have A of H is a subset of H. Okay, so let's let H be an H. Okay, let H be an H. Then, since A is an H, and of course we just said H is an H, we know that A inverse H, right? A inverse H must be in H. Okay. Then H would be equal to E times H, which would be equal to A inverse times H, which of course is A and then A inverse H, which we know is in AH. Okay. All right. So we have AH is a subset of H, and H is a subset of AH, right? That implies that AH equals H. Okay. So that's how we get that one. It's a little trickier going the other direction, but I think we get it. Okay. Very good. Let's jump to item 3. What about number 3 here? So 3 says that AH equals BH, or AH and BH are disjoint. All right, so either the intersection is empty between these two sets, or they are the exact same sets. Okay, so let's assume for this, let's assume that AH and BH does not equal the empty set. Okay. And let's let X be in that intersection. Okay. Then, so we're assuming that the intersection is non-empty and that X is an element in that intersection. Okay. So if X is in that intersection, then there's going to exist H1, H2 in H such that X is equal to A times H1 and X is equal to B times H2. Okay, that's just, because X is going to be in the intersection of both of these, so it may not multiply with the same H, but A times H1 and B times H2 must be the same if they're in the intersection, they're both equal to X. Okay, and so if that's true, then, well, we've got our A is equal to X H1 inverse, right? So just kind of do a little bit of work on this, which is equal to BH2, so X is BH2, H1 inverse. Okay. And A times H is equal to, let's see, B, yeah, so this mess here times H. Okay. Which would be equal to B times H2 H1 inverse H, which is equal to B times H. Now, what am I doing here? Hold on. Well, this is by property 2. Okay, remember property 2? Right, property 2 said that AH equals H if and only if A is in H. If and only if A is in H. Okay. So that works. That's how that comes about. Very good, very good. All right. Let's jump to 4. Let's jump up to 4 here. So 4 says AH equals BH if and only if A inverse B is in H. Okay. Well, this one actually follows directly from the previous example. Well, from property 2 actually, because notice if I have AH equals BH, then that implies that that implies that H is equal to A inverse BH, right? Which is basically the result here. And so this follows from property 2. Okay, just like the previous one did. Okay, how about item 5? Item 5 says that the size of AH and the size of BH are the same. The orders are the same. Okay, so how can we do this? Well, one of the best ways to see this kind of thing is to think about it from the standpoint of a map, right? Right. So note a one-to-one mapping exists, right? And the one-to-one mapping says take the element H from AH and map it onto BH. And this is going to map AH. Obviously, this maps AH to BH. Right? So it's obviously one-to-one, but is it onto? Well, it has to be, right? Because every H is accounted for on both sides, right? If I take a random H over here, then I know exactly where it's coming from. It's coming from AH, right? If I have an H1 over here, BH1, well, that's going to come from AH1, right? So it's not just to BH, it's onto. Right? So I've got a one-to-one and onto mapping. That means that they must be the same size. Okay. Okay. Now the one-to-one, hopefully you can see that, right? If AH equals BH, then AH, H inverse equals BH, H inverse implies A equals B, right? So it's really straightforward to see that. Okay, how about 6? 6 says that the left and right cosets are the same if and only if H equals AH, A inverse. Okay. Right, so let's just do it this way. Let's say AH equals HA, and we can say that's true if and only if AH, A inverse, equals HA, A inverse, which would of course be equal to HA, A inverse, which is H. Right, so you've got that equals that. Okay. Now this idea of, because we didn't start with both ends of the statement, we're just kind of saying AH equals HA if and only if this is true, and then you get the equality and the results you want. Right. So hopefully that's clear. It's a little bit of a speedier way to do it, slightly. Unless you have to explain it, then it's less. Probably would have been more efficient to do it the other way. And then the item 7 says that AH is a subgroup of G if A is from H, right? If the element generating the coset is from the set H. Okay, all right. So So if AH is a subgroup, how do we prove this? So if AH is a subgroup, then E must be inside of AH, right? And that's going to imply that the intersection of AH and EH is not empty. Okay. And then by property 3, we have AH equals EH must be equal to H. Okay, because they're both from H. Okay. And then by property 2, we have A is in H. Okay, right? So if we start with the idea that AH is a subgroup, we get A is in H. Now, conversely, if A is in H, then we can again call on property 2. All right, remember what property 2 says? I keep using it and make sure we know. AH equals H if and only if A is in H. Well, if A is in H, then obviously AH equals H. Okay. All right. Perfect. Okay. All right. Let's keep moving. Let's see what else we can do here. All right. Now I think these are tricky enough. They seem tricky on the surface for sure, like when you're first learning about these, because it's hard to pin down what these things are. But I think the previous properties can be restated in a way to make it a little more obvious what we're doing here. Cosets are tricky, but not that tricky. What are these things actually saying? Okay, what is the first property saying? Right, property 1 just says that A is in AH. Well, what does that mean? In plain English, what does that mean? The left coset of H containing A does contain A. That's what that means. The left coset of H containing A does contain A. Okay, what is the second property? The second property says that AH equals H if and only if A is in H. Now, what does that really say? What it's saying basically is that H will absorb an element if and only if the element belongs to H. So H will, and this is like pretty loose terminology, absorb, right? AH equals H. It will absorb, H will absorb an element if and only if the element belongs to H. Right, if you take an element from outside of H, then H will not absorb it, and the set will change, and you won't have AH equals H. And that's the idea behind that one. What about the third one? AH equals BH, or the intersection is empty. What does this mean? Well, what it basically means is that two left cosets of H are either identical or totally different, or disjoint. So two left cosets and right cosets as well are either identical or disjoint. That one's fairly straightforward. What about 4? 4, we said AH equals BH if and only if A inverse B is in H. Right, what is that one all about? Well, this one can't be summed up in a nice little neat expression, but basically what this is doing is showing us how we can how we can transfer a question about equality, AH equals BH, to a question about H itself, right? So if I want to know if two cosets are equal, I just need to know if a particular element is in the set itself, the set H, right? So this is handy when you're trying to, sometimes it's in math. It's very often the case that you just have to translate a question into a different question that's equivalent, and that's what this one is doing. Okay. What about 5? The size of AH equals the size of BH. Well, all of the cosets of H have the same size is what this is all about. All of the cosets of H have the same size. Okay. And 6, AH equals HA, if and only if H equals AHA inverse. What are we talking about here? Well, this is a similar to, this item 4. Here we're transferring a question about equality of cosets of H to a question about H itself. If I want to know if the left and right cosets agree, I just need to know that a particular item is in H. Okay. And let's see, the last one, let's think about how we can restate this. AH is a subgroup. It's a subgroup of G if and only if A is in H. All right, so what can we say about that? Well, H itself is the only coset of H that is a subgroup of G. Okay, and so this one is very tightly connected to property 2. So in property 2, we saw that AH equals H if and only if A is in H, right? So AH, which is H, is a subgroup of G if and only if A is in H. The only time you're going to get a subgroup from a coset is if the coset is equal to the subgroup you're starting with. So what it's saying is that H itself, right? H itself is actually the only coset of H that is a subgroup of G. H itself is the only coset of H that is a subgroup of G, right? You're not going to get other cosets that are not equal to H. There may be other cosets that you could start with, but you would find that they resolve down to being equal to H. Right? You're not going to find a coset that's distinct from H that's also a subgroup. Okay. All right. Very good. Okay. So let's notice a couple more things here also with cosets. Notice a few more items here. So 1, 3, and 5, they all guarantee that the left cosets of a subgroup H partition G. We'll say left cosets, but it's also true of right cosets. So items 1, 3, and 5 guarantee that the left cosets of H, of a subgroup H of G, partition G. Okay, right? And not only do they partition G, but they partition G into blocks of the same size. Right, so they actually partition off G into very specific blocks. right? And all of the blocks are the same size, right? So we saw this with, for example, we had H was 0, 3, and 6 in Z9, right? And we found that the cosets, there were 3 cosets. The first one was 0, 3, and 6 itself. The second was 1, 4, and 7. And then the third was 2, 5, and 8. Right, so these are, they form a partition of Z9. Remember what Z9 is 0, 1, 2, 3, 4, 5, 6, 7, 8. Right, and so these partition Z9 down. Right, so this one here was 0 plus H, remember, and it was 3 plus H and 6 plus H. This coset here was 1 plus H, and it was 4 plus H and 7 plus H as well. And then this one over here was 2, 5, and 8. Okay, right, and so we were able to partition Z9. Right, so we can think of the cosets of H as a partitioning of the group G into equivalence classes. Okay, so the cosets partition G into equivalence classes. And what do we mean when we say equivalence classes? We better give some kind of a, what's the relation? Well, equivalence classes under the relation A is equivalent to B if, and only if, AH equals BH. Okay, so up here, for example, 0 and 3 are equivalent because 0 plus H equals 3 plus H. Right, 1 and 8 are not equivalent because 1 plus H is not equal to 8 plus H. So that's, they fail that equivalency. Okay. All right, I'm gonna end the video here, and then we'll have a part B where we'll get into Lagrange's theorem. Okay, so we'll end the video here, and in part B we'll pick it up.